For this lesson, you need a breadboard, you need a bunch of wires, and then you need probably 3 or 4 LEDs. Now, they don't all have to be the same as mine are. They can be different. It works equally well. You also need some resistors, and so all of the ones that are shown here are all 100 ohm resistors, but you can use other resistor values and get good results as well. And then you also need a 9-volt battery and then your microprocessor. And so what we're going to do is we're going to look at the laws that are governing voltage, current, and resistance and try and think about them from a series versus a parallel standpoint. So to begin with, I have some LED light bulbs that are connected in series. Now it may be a little difficult to see how this is series. So if you follow the red will take you to this resistor here, which is in a pin. That pin goes into the positive lead of this LED. Then the negative terminal of this LED leads to the same row as the positive terminal of this LED. The negative of this goes to the white wire. The white wire takes you to the positive terminal of this LED, and then the negative goes to this black wire, and black wire goes to ground. So the idea here is how many light bulbs maybe can we light up in series? And that's going to depend a lot on our voltage. But before we get and we answer that question, let's look at some of our assumptions that we're about ready to make, as well as the math behind the ideas of a series circuit. These blue LEDs that you see right here are the ones that I'm using in this video. And so you can see their voltage is approximately 2.8 volts to approximately 3.2 volts. And so we're going to make an assumption of about 2.8 volts. And then this 20 milliamps, that's going to be related to the current that's going to be needed in order to cause this LED to light up nice and pretty blue. So here is a circuit diagram showing us Kirchhoff's laws. So if we've got series, we have basically a loop, a current loop. We have our series drawn here with your resistance of 100 ohms shown right here, and then you have various LEDs. Now I just drew 5. You can draw as many as you think you need to draw in your series. Now what Kirchhoff's laws is really going to emphasize for series is that the same current is going to make it to each LED. So in a series, in a loop, your voltage total is going to depend upon the sum of all the individual voltages. And so we're going to use that concept here in order to determine how much current can pass through each LED. So we know Ohm's law, voltage equals current times resistance, and we rearrange that and solve for the current passing through an LED. We can make the assumption that if we're going to use a 9-volt battery, it's going to have 9 volts. Now we'll think that may not exactly be true, but it's going to be close. And then we're going to assume 2.8 volts for my LED, and then the resistance of my LED is going to be negligible, which means that if I take my current for an LED, I can determine what that is by taking the source voltage, that of my 9-volt battery, and subtracting out the voltage of each individual LED. Then I divide that by my resistance in my loop, and if I assume the resistance of my LED is negligible, that resistance becomes my resistance of my resistor. If I have 2 LEDs then, 2 LEDs means I have a 9-volt battery minus my 2.8 twice for each of my 2 LEDs divided by 100 ohms of resistance. That means I should have 34 milliamps of current, which that is greater than my 20 milliamps that my LED says they need based on the box. And so 1 LED, 2 LEDs, either of those two should light up fine. But what if I throw in a third LED? Should I get my LEDs lighting up? Well, 6 milliamps is less than 20 amps. So we'll see. What about 4? Now we're getting a negative number. Whoa. So it's a big question. Do we really think that these are going to light up? So let's take these assumptions and these mathematics and figure out how many LEDs can we light up? 1, 2, 3, or 4. Back to my breadboard now. I'm making sure that I'm going to light up the positive side on the plus, and the negative needs to be connected here to the negative side of my terminal. And we can see that no, those are not getting lit up. But my battery, how much voltage does it really have? For that, I want us to pull out a voltmeter. And if you don't have one, I didn't include this in the list of things that you need at the beginning of the video. So don't worry too much about it. I'm going to turn my voltmeter on, and then I'm going to place my probes here onto each of the terminals of my battery. And you can see this is not a good battery. It's actually lower than it was a minute ago, 6.67 volts. So it's not a good battery. So I really don't have a good one there. Let's test out a different, similar battery. Let's see if this one now is going to be 9 volts. And it is 9.62 volts. So this battery is good. So maybe it was just that my battery was bad. Let's see. But even then, 3 should not be lit up by a battery. But we actually do get some. Why is that? Well, maybe some of our assumptions were poor, or maybe what we learned in our previous video is true. That as long as some current is flowing, we should be able to get some brightness out of those LEDs. To test that theory, let's use 4 LEDs and see if we can still get it to light up using this battery. I have now added a 4th LED into my mix. And I'm going to see if I light up. You can tell it's even lower now. All right, well, let's try a 5th one. Let's see what happens when we add a 5th LED to our circuit. I've now added a 5th LED to my circuit. Let's see if now we can finally make it so that our LEDs do not light. And as you can see now, they do not light. And so the question is, what happened? Why were we able to light it? So if we look back at our assumptions, we can see that maybe the LEDs did not need 20 milliamps. Maybe our 9 volt battery was not exactly 9 volts, which it was higher than 9 volts, but not that much. Okay, and then also the idea that maybe there is other functions that we need to consider in our circuit. So if we look back at this, this gives us a good estimate to let us see that as you increase the number of LEDs that are incorporated in a series, you're going to decrease the current that's passing through each one of your LEDs, because the same current must pass to every single LED. Your voltage total is equal to the sum of all the voltages, but your current is the same voltage in the loop, regardless of which LED it's looking at. And so if one fails, they all fail, which when you think about Christmas trees, this is something people know all too well. So kind of another way of looking at these Kirchhoff laws for series is that voltage is divided in series. So meaning your series, the sum of your series, if you represent 3 individual resistors with a single resistor, it's going to be equal to the resistance if you add all 3 of the other resistances together. All right, let's look next at parallel. So now we are looking at a parallel circuitry where we've got your positive going to this terminal. Every single LED has a 100 ohm resistor in front of it, and every positive terminal of the LED is connected to the resistor, and the negative terminal is connected to this wire, which goes to my negative bar. So now you may be thinking, well, with the previous setup, we weren't able to get all 5 LEDs to light. Why would I get them to light up now? Well, let's try it and see what happens. And as you can see, it has no problem lighting up. And if I switch out my battery for the other battery that wasn't as good, I bet we'll even now be able to still light it up, and we will. So with this, we can see that whenever you combine a load in a parallel versus a series, you're going to have different mathematical properties that are going to dictate how current and voltage throws through the circuit. So here are Kirchhoff's laws for parallel. The idea that you draw a circuit and it's parallel, but your current is going to be divided. So meaning you have the same voltage now that's going to go to every single LED instead of being a total voltage for the loop. And now your loop is going to be total is equal to the sum of all your individual currents. And so the idea here is just down here is if your current comes in, it's going to get split. Okay? Your current is going to get divided. So if you were to represent a single resistor or 3 resistors by a single resistor, it's 1 over your resistor in parallel equals 1 over each of your individual resistors. And so will a 9 volt battery light up 5 LEDs? The answer is yes, but only if they're in parallel, because your current is now divided. And so that's going to make it so our LEDs will in fact light up. Now we can test this with an Arduino and see if maybe our parallel, since it doesn't need as high of a voltage input, see if we can't light it up with our Arduino. All right, I have the same parallel circuit as before, and I'm going to use my black wire to connect to ground. And my red wire, I've got a couple different options. If I want it to blink, I could use a sketch and choose any of the different inputs that I want, or I could, this one right here is a 3.3 volts. So I could connect here, and you can see that in parallel, my 3.3 volts is sufficient to power all of these LEDs. Whereas if I plug in my series, I will not be able to power it with 3.3 volts. And so this is really important parameters when you're doing instrumental design, because just by connecting something in series, when you meant to do it in parallel, you could make it so none of your stuff works. And so how you draw the circuit diagram matters, and thinking through, is this in series or is it in parallel? And that will help you figure out how to wire stuff whenever you're working on your instrument.